Okay, we have an announcement to make. Please, one of your colleagues lost his iPod, and if any of you found it and didn't have a chance yet to turn it back, it would be a great thing. I'd take it, or you can just deposit it in the back there, and I will give it to him. Here he is. Come on. Come on. Come here. Tell me your name, and tell them, make your plea for the iPod.
Plea for my iPod. Hi guys, my name's Samuel. I lost my black iPod Touch. It has a black silicone casing on it, so if anyone finds it, if you can turn it into the professor, that'd be great. Thank you. Oh, it was near the top.
How many gigs did it have?
I'm not going to tell you.
Okay, funny for me, but not funny for him. It's not funny that he lost it, but with the gigs, I think. Never. You always misread me. Not always. Are they ever going to fix this here? They're working on it? Since 8 weeks? Wow. Okay, great. Thank you. Who was the voice of God up there? Okay, good. Okay, I think I'm live already. Full of energy, just like you. Good afternoon. The last time we've been struggling with acids and bases, and strong acids are rather simple to understand. You put 0.1 mole in a water solution, in water, and you make a 0.1 mole per liter solution, then you have a 0.1 mole per liter solution, and the pH is that it dissociates completely into HVO+, and whatever anion that acid has. So if it's HCl, it reacts with water, makes HVO+. I'm pointing towards the right side because the equilibrium goes to the right side. It completely dissociates to HVO+. Actually, I should point this way because they're always written this way for you, okay? It goes into HVO+ and Cl-. We have seen two things. This is a strong acid that completely dissociates. There's nothing left on the left side, okay? And then it also conducts electricity because you have this chloride ion in there. And so what is the pH of a 0.1 molar HCl solution, strong acid solution? What's the pH? 1, okay? You take the logarithm of 0.1, multiply with -1, then you have the pH. The pH of a 0.1 molar weak acid solution is not 1, and we went through this the last time. We calculated this. It is larger than 1 because you have on the left side still a lot of undissociated acid here. You see that? It doesn't make quite as much HVO+ than if you would have a strong acid. A strong acid, you have a very large K. That means this is very large and this is very small. This is the opposite, or this is not very large, and this is much larger here for a weak acid. So with this, you have a pH that is higher than 0.1. Of course, you can make a weak acid solution that has a pH of 1, but you need a lot of weak acid to do that. You need a lot more than 0.1 moles per liter, okay? So because it doesn't dissociate like this. So your pH initially is higher, and we calculated this. I think it was 2.88 for acetic acid. Yeah, I don't think so. I know actually it was 2.88. All right? And then we talked about what happens if I dilute a strong acid solution. So I have a, let's see, what was the question I have? I have a solution of HCl. This is a pH of 3. What is the HVO+ concentration if I have a pH of 3? It's 10 to -3 moles per liter HVO+. Moles per liter, okay? Now if I dilute this by a factor of 10, What's the concentration, just the concentration in moles per liter of the H3O plus now? What is it? 10 to minus 4 moles per liter. You did not change the amount of H3O plus. There's no change of the amount, but you diluted it by a factor of 10. And since the concentration is given in moles per liter, that way you diluted it by a factor of 10, and your molarity went down by 1 order of magnitude. It's now, instead of 10 to minus 3, it's 10 to minus 4. And with this we had said that the pH is what? The pH is 4. You take the logarithm of 10 to minus 4 molar H3O plus, the logarithm, that gives you minus 4, and you multiply it times minus 1, that's 10 to minus 4. No, this is pH 4. That's pH 4. Let's do that again. We have a 10 to minus 3 molar solution. We dilute it by 10. We have now a concentration in moles per liter of 10 to minus 4 H3O plus. We want to know the pH of the solution, and this is a strong acid solution. We take the logarithm of this, multiply by minus 1, you get 4. Okay, that pH is 4. Now, that was the first question I asked you the last time. Now let's take a weak acid and dilute this by a factor of 10. What is the new pH? Is it smaller than 4, equals to 4, or larger than 4? We are now at B. That's a weak acid. Okay, why don't you think about this and give me your answer, please? So you need to look at this equilibrium here. What did you add? I didn't dilute it, I'm sorry. It's a weird answer. Very weird answer. It's a weak acid. You dilute it, and it goes in the wrong direction. I say no more. Somebody must have elephant ears here. Okay, did I ever start this? Oh, okay, good, thank you. Just asking. All right, so this is not clear, that problem. And I think you need my help. So we agree when you have 10 to minus 3 moles per liter of H3O3 plus in solution, and you dilute this by a factor of 10, you have instantaneously, at this moment, you have 10 to minus 4 moles per liter in solution. But it doesn't stop there, because it's a weak acid, and that weak acid sees suddenly a whole bunch of water, lots of water. So what will it do if it sees all this water? Obviously, it's out of equilibrium. It tries to get back to that constant here, get into equilibrium. What does it have to make in order to get back in equilibrium? And so if it does make that, is the pH then smaller than 4, equals to 4, or larger than 4? Why don't you discuss this with each other and give me a good answer? You increase what? Yeah, okay, that's good, yeah. All right? So what does it increase? What does it do to pH? No. Yes, Henry. Yes, HC is a weak base. That's what I said. We have, of course, a weak base. What? AC is a weak base? Who says that? Yeah, it's a weak base. But this really doesn't matter, in this case. The equilibrium was right up there. You don't have to really use your head that much. So this is your equilibrium. Look at it, just look at it. And you put this water in here. So where are you then? Are you going in this direction or in that direction? Depends how you're standing. If I stand like this. He said to the right. Yes, it does, if you look at the equation. We are done already. Wow. That didn't help at all. Okay, so he does all this dancing around here, so it's not going to be 4 because it was 4 before. Now, is it higher or lower? I really don't know, some of you say. I go with, let's go with higher. It's weak acid. pH is higher. No, it's not, okay? And so I think you need to get this right. I'll give you another minute, okay? You need to get this right. Get it in your head. What happens if you add water? You have this equilibrium, you add water. Does it make more of this or does it make more of that? Okay, your acid concentration goes what? Up or down? Up. What does the pH do? Okay, why don't you vote for one again, okay? I give you 30 seconds. But know why you're voting what you do, not because your neighbor said so. Discuss it with each other. You need to get that. There's going to be a final. There's stuff like this on there. Yeah, there will be a final, actually. They just told me. Yes?
How come you said that if for this one, if it's a weak acid, then the pH is greater than 1?
Yeah, that's a different story. I didn't add. So, when they are done. So, somebody asked me here, when we were talking about a 0.1 molar weak acid compared to 0.1 molar strong acid, how come that you said that the pH was greater than 1 for the weak acid? Yeah, because you haven't dissociated as much HVO plus for the weak acid than you did for the strong acid. So there's not as much HVO plus on the right side than if you would have the strong acid. But here, that's a different story. That's just at equilibrium. So if you have a strong acid, that would be HCl, for example, you go all the way in here, HVO plus and Cl minus, and this would be a constant larger than 1, much larger than 1. With this equilibrium would be on this side. You have hardly anything left in a strong acid. So this will determine the pH in your strong acid. If you have a weak acid, you have a lot of this left here, and you made very little of this here. So you'd put in 0.1 moles in 1 liter, but it didn't dissociate. So with this, you have less of HVO plus. With this, the pH would be larger because the constant is the negative logarithm. Okay. So, but this is not our question. Now the question was the acetate, the acetic acid. I put it. I dilute a pH 3 solution by a factor of 10, and initially I get pH 4. But this is not the final stage for the weak acid, because you have all this water here, and the water reacts with the undissociated acid and makes more H3O plus. With this, the H3O plus concentration went up. But if your pH, if the concentration of H3O plus goes up, the pH goes down, okay? The lower the pH, the higher the acid concentration. Let's see what this, oh, excellent. Look at that. We got it. Perfect. Whoa. Okay, so this was the first one with the strong acid, and now the weak one comes here. That was the weak one. Initially we have 10 to minus 3 molar. That's why we have pH 3. That's all there is. The log of this minus 1 is 3. Now we diluted. Initially we have a lot more than 10 to minus 3 of the AC here. We diluted. We have initially 10 to minus 4, but that's not the end of it. 10 to minus 4 mole. Now we react with this water because we put a whole load of water in there. The undissociated acetic acid, the weak acid, reacts with the water to make H3O plus the acetate ion. With this, the H3O plus concentration goes up, and the pH will be lower than 4. Okay, produces more H3O plus, and this is smaller than 4. Okay, this was a tour de force. All right, so today we're going to continue and talk about titrations of a weak acid with a strong base and vice versa. And we have established this. This was your question here. What's your name again? Liz's question here. At the beginning, when she said, how come the pH here is higher than if you had a 0.1 molar strong acid? Of course it's higher, because we haven't added any water. That's just the equilibrium, okay? So, and now we're going to look at two other regions. That was that region C here, and that buffer region B. So region C, what's going on? Region C would be this here. Let's see if I have this here. Yeah, region C I have here. Whoa. Region C. So we want to calculate region C here. So there we have the equivalence point. Okay, this is when we molecule per molecule, H3O plus was neutralized with OH minus. At the end, at the equivalence point, we should, for a strong acid, we should have pH 7 because we have water, just water. But with these darn weak acids, we have now this to deal with that acetate ion. No, that's the wrong thing here. The acetate ion, too many handles here. The acetate ion. So this acetate ion reacts with water again, okay? And now we are at the neutral point, but there's water around, and it reacts to form undissociated acetic acid plus OH minus. Of course, it's a lousy base. Look how big that base constant is, all right? That's what Henry said. It's a weak base, okay? And how small that base constant is, but it still makes some OH minus. So let's calculate this now. What would we expect? It would be not pH 7, because it's a weak acid that we titrate with a strong base, and we get to the equivalence point, but then it starts reacting with the water, and it makes OH minus. So the pH should be larger than 7 and smaller than 13, of course. All right? So let's calculate this. How much acetate did we have? If it was 0.1 molar sodium acetic acid, it's totally dissociated. What's the concentration of the acetate ion at this point? 0.1 molar, because you moved everything to the right here. So this is 0.1 molar. You started out, this is 0.1, and this is 0.1 molar, okay? Now, so you have 0.1 molar acetate. So, and we call this here, let's say this concentration, we want to find out what this concentration is to calculate the pH, yeah? This concentration is X, and this would be X, and this was initially 0.1 molar, but it reacts here to form this and that. So we say that's 0.1 minus X, and we call this X and X. With this, we have our equilibrium. We know what that constant is. That constant is 5.6 times 10 to minus 10. All right, that's that equilibrium. So we say X squared, this is this concentration times this concentration, divided by 0.1 minus X, gives us our constant, and the number we know, so X squared point minus X, is 5.68 times 10 to minus 10, okay? Now with this, now we can solve this. We can solve it either the long way, or we make an assumption. We say because that constant is so small, there's only a very, very small amount forms X. So 0.1 minus X is about 0.1. We can assume this because it's so little, yeah? So we say, okay, this is X squared divided by 0.1, so X squared times 0.1 times kb, no, x squared equals 0.1 times kb, and this is 5.68 times 10 to the minus 10. So x is 7.5 times 10 to the minus 6 if I take the square root out of this, multiply it. So the square root of 5.68 times 10 to the minus 11. That's a 7.5 times 10 to the minus 6. So that's the concentration of undissociated acetic acid, and that's the concentration of OH minus. What happens if I take the log of this and multiply it with minus 1? What do I get? The P what? No. The P what? POH, because this is the OH concentration here. So somebody take your TIX 5 million out and calculate that for me, please. So you have 7.5 times 10 to the minus 6. What's the log of this? Anybody? 5.12. Henry, you have come to aid me. Thank you. 5.12. Is that 5.12? No, it's minus 5.12, isn't it?
No, it's negative log of the x.
So I ask what the log of this is. What's the log of this?
Oh, it's negative 5.12.
Minus 5.12, that's the log. We multiply with minus 1. Then we have the POH. The POH is 5.12. So pH plus POH equals pKw. So pH equals pKw, that is 10 to the 14 or 14, minus POH. What is the pH, Henry? 12, 14 minus 5.12 is what? I help you. It's 8.88, okay? The pH is 8.88. There it is, Henry. Okay, thank you. pH is 8.88. Be careful, not just what you calculate. We calculated here the OH concentration. So this is actually the equivalence point, 8.88. That's the pH at the equivalence point because of the reaction of the weak base here with that water. All right, now we're talking about, this was region B, so we talked about region A, that was the initial pH, then the equivalence point, what happens here, that was region C. Now region B is the buffer region. If you look at this here, so we have here, this is the equation, and we're talking about acetic acid, and we titrate this with OH minus, okay? So what we do, we take OH minus, sees this H3O plus, ion by ion, and makes water. What happens if I take this out here and neutralize this to water? What happens here? What does it do? Chatelier at work, okay? It makes more H3O plus. So I obviously taking away the H3O plus with the OH I'm putting in there, and not much happens because it immediately makes that same H3O plus again, and so I don't see much of a change. This is why this curve here is relatively flat. There is not a whole lot of change when you start adding. You see, you add here your base, you add it here, this is 0, and you add more and more base, and very, very little happens, okay? So you come to several points here. When you have this concentration equals this concentration, okay? What is that point? That's the half equivalence point, where half of it is used up, this one, okay? That's the half equivalence point, and this usually gives you, let's see, it gives you nothing, okay? So I have this again here, that's the half equivalence point. Where is it? It should say pKa. So this gives you here the pKa, okay? The half equivalence point gives you the pKa. So now you look at this here. At this point, the concentration of the undissociated acetic acid equals that of its conjugate base, the acetate ion. This would be here the half equivalence point, and with this, if you go over here, you can read off your pKa, all right? So what happens, so if I continue here, that's what I'm looking for, okay? So now we have just this branch here, and now it appears there is a slight slope. You see that? There is a slight slope, but compared to the overall titration curve, that's rather flat. So the pH does change slightly, but not a whole lot. So this is called the buffer region. And we are here at the half equivalence point, and then we come to the pKa. And on this side here, this concentration divided by this concentration, no, this concentration divided by this concentration, this is smaller than 1 because you have more of this here, okay? Now, if you go, this is called the acidic side. The acidic form predominates. This is the acidic form. And now, if we go past this point, you see you have more of this here and less of this here. That means that will be that quotient here. That quotient will be larger than 1, okay? And this is called the base form predominates. That's the conjugate base. That base form predominates. And so essentially a buffer works from pKa minus 1 in the acidic form to pKa plus 1. So it goes plus minus 1 pH unit. That's the useful range of a buffer, okay? So what is a buffer? You can have a basic buffer or an acidic buffer. So a buffer is essentially a weak acid, and it has an equal concentration to its conjugate base. So you take, for example, 0.1 molar acetate and 0.1 molar of acetic acid and mix those together, then you have a buffer. And you can now calculate your pH as you keep adding acid or base, okay? So why are buffers important? Actually, our blood, anybody knows the pH of our blood? The pH of our blood is 7.4. And it is very, very sensitive to changes in pH. If you change it by 0.3 to 0.4 unit, you die pretty quickly, okay? So blood buffering is a very, very important issue in our physiology. And we eat, of course, we eat acidic stuff, we eat basic stuff, you drink wine, you drink beer, beer is a little more not so acidic as wine, you take vinegar and all kinds of stuff in your salad, and the body has to deal with all this, and so there's quite a few buffers set up in our system, and one of them is the blood buffer, and so that's why you need to know how a buffer works. So the pH of a buffer depends on the pKa or the pKb of your acid or base. You can also take a base, a weak base, and take its conjugate acid, and then it would go that pKb plus and minus 1 would be the useful range of the buffer, okay? So if you want, for example, a buffer that is around pH, let's say, what is that, pH 4.7, okay? We want a buffer, the region 4.7. You take a 1 molar or 0.1 molar acetate solution. You may take acetate and acetate salt, make it 0.1 molar, and then you make a 0.1 molar acetic acid solution, and you mix them together, okay, so that they are both in the same volume. So we have each of them is 0.1 molar. And now the pH would be the pKa, that would be 4.7, and I showed you that can be plus 1 and minus 1. So it goes from 3.7 to 5.7. It buffers very nicely, okay? So you look up in a table, you look up your values for pKa's or pKb's and take the conjugate acid or base or the acid, depending if you have an acid or a base as the buffer, and then you can make the buffer for that pH region. This is how a buffer works, and I want to show you this a little bit. And let's see, we have, you know all, I better put my glasses on. You know this here all, isn't it? Remember that? Okay, what is it? CO2, we can play CO2 hockey, okay? That's not the, so what is it? It sublimes, doesn't it? No, it doesn't sublime. Is it subliming? Okay, good. So what does that mean? It goes from the solid state to the gas state, and we talked also about Henry's law, so it dissolves in water. And so you have CO2 is in equilibrium with CO2 gas, and if you put the CO2 in water, you make H2CO2, carbonic acid, and this H2CO2 reacts actually with water to make H3O plus and HCO3 minus. See, there's still an acidic. One of the protons left it and went to here to make this here. And so you see this is already acidic. But this here reacts further with water, and then it pulls off that second proton here to make this H3O plus. I forgot the water here, okay? We need to put in water. It's sloppy, okay? Plus water makes H3O plus CO3 2 minus. So it's a diprotic base, and we talk about this the next time. So you know carbonic acid, as the name says, is acidic. And we have now, if I could have the camera on this here, please. We have a pH 11 solution of sodium hydroxide. Sodium hydroxide, and we have a universal indicator in there. It's beautifully magenta at this color. And then we have another one, just to compare it. And then we have a buffer solution at pH 11, so which is a phosphate buffer, okay? And so I want to like to ask you a chem quiz. So I'm going to add here, I'm going to add to the sodium hydroxide, I just shovel in some CO2. What will the pH do? Will it go A, larger than 1, larger than 11, A, B equal to 11, or C smaller than 11? If I put this carbon dioxide, solid carbon dioxide in there. So A, larger, B equal, and C smaller than 11. Why don't you answer that, please? A larger than 11, B equals to 11, C smaller than 11. If I add this carbon dioxide here. You can discuss it with each other. Not everyone at once, please. So you have a base, and you add what to it? Okay, what happens to your pH? Don't go in the wrong direction. So pH 0 is very acidic. pH minus 2 is extremely acidic. pH 2 is acidic. pH 3 is acidic. Wine has about pH of 3 to 4. White wine more than red wine. Higher pH, lower pH for white wine. Oh, I gave it away. So the question was, we add solid CO2 to the sodium hydroxide solution, which has a pH of 11. Was it small? Does the number get larger than pH 11? The same, pH 11, or lower than pH 11? Okay. Alrighty, why don't we have a look at this? So the majority says C, but there are quite a few people says A, and then because he asked the dumb questions, let's say B then, okay? Okay, so you said C at this point. This is a universal indicator. If I could have that picture, please. You ready? Okay. So we're going to add this here. See that? It immediately gets blue, and then it gets red, and then it gets yellow. Yellow first, and then red. Let's have a little fun with this here. Ooh. What does this mean? It goes from blue to red. That's a universal indicator. Red stands for acid, okay? So, of course, you are just titrating it with these H3O pluses. It releases these H3O pluses, and they neutralize the OH minus. And with this, they will, you see that here? You put this together, the H3O plus the OH minus makes water. And then you put more in there because I put a whole load of this in there. So I'm making even more H3O plus, and it becomes acidic, as you can see here. It also looks pretty, all right? So now we have a buffer. Look at that. Isn't that beautiful? Huh? Now we have a buffer, and this is pH 11, the buffer. And I'm asking you if this is, if I add the CO2, so that is carbonic acid, as we have established, does the pH go up? A, does the pH stay the same? B, does the pH go down? C. Why don't you answer this, please? That's a buffer. Looks beautiful, huh? Like chemistry in the movies. And there's this wild guy with the wild hair, you know. So, give me your answer. You need to know how buffers work and what buffers are. If you go into nutritional science or whatever policy, any politician needs to know what pH and buffer is. They don't, unfortunately. But they talk about everything. Don't know anything, but talk about everything. That's nearly like a professor. Oh, I didn't say that. Okay. Can we cut it short? Yes, everybody in? Last second. Okay, we stop it and we display. That takes alone 5 seconds because his memory is so slow. Okay. So what does a buffer do? What was it again, a buffer? So a buffer is actually insensitive to changes in pH. You can add OH minus. It makes more H3O plus, or you can add H3O plus, it makes more OH minus, okay? So nothing is happening, it buffers it, and with this, the pH should stay what? I give you another 30 seconds to answer this again, because I don't want to hear that you don't know what a buffer is, okay? 30 seconds. We have a phosphate, hydrogen phosphate buffer at pH 11. So, 15 seconds, you tell me if the pH goes above 11, stays at 11, or goes below 11. So, click in, last 10 seconds. Everyone, quick. I need to count you. Give me your answer. Wow. That's fantastic, isn't it? The buffer stays, doesn't do anything. Let's see if this is true. It stays the same pH, okay? I say it's true. And let's see what the experiment shows us. Are we up there? Good. See that? Nada. Niet, niente. Nichts, nothing. Okay, rien. That's what a buffer is all about. Of course, you're exhausted if you put this load of stuff in here, okay? You will exhaust it eventually. But it's fighting to keep that pH constant. See that now I'm trying to destroy the buffer, okay? It still is blue. Can you imagine? It's fighting. Okay, so you can watch this a little later then. That is a very good shot up there. Thank you very much. And so with this, we're going to go on and talk a little bit more about buffers. So the buffer range is pH is pKa, whatever, or pKb, times log A minus, if you use an acidic buffer, A minus divided by HA. Remember, you had buffers when you were calibrating your pH electrode. You had a buffer of 7 and a buffer of pH 4. And you said, I know this is pH 7, this is pH 4, and so I adjust my instrument, and now I can measure anything between 7 and 10, or 7 and 4, precisely. So if we now, if this concentration is 10, so that means this is 10 times more than this here, that would be log of 10 is 1. Okay, this is about the limit. So that would be the range for the pKa. pH is pKa, this would be to the pKa plus 1, that would be in our case 4.7 was the pKa for the acetate buffer, for example, would be 5.7. And then if this ratio is 0.1, so this is 10 times more than this here, then the pKa would be, pH would be pKa minus 1. And so what happens if I dilute this buffer? If I dilute this buffer, let's see, I dilute the buffer by the factor of 10. So it's still fighting. It's still not acidic. It still keeps buffering. So if I dilute the buffer by the factor of 10, what happens? Is it still work or doesn't it work? So you take a 10 here and you divide by 10 here. So that looks like this. Is it still a good buffer? Of course, because this cancels out here, and with this you have the same equation again, and the change in pH will be close to 0. There will be no change in pH essentially, or some really noticeable change in pH. So this is the Henderson-Hasselbalch equation that I've been writing to death here for you. I always call it the Henderson-Hasselhoff equation. This is a guy who was famous. Actually, he's popping up again on television. He was famous many years ago. There was a show, I was on the beach and so on. Many people said, oh, it's very interesting, and especially a lot of males watched this. And I don't think they watched it because of Hasselhoff or Hasselhoff. And so then he disappeared, and he was, I don't want to say something about the quality of his acting, but he disappeared. And I was in Germany many years ago, and he's a superstar over there. The 11-year-old girls, they go totally crazy over this old man, okay? And he's about my age, can you imagine? And so I wonder, he looks a little better than I do, probably. But I was always thinking, oh my God, look at this there. And then they admired this old person there. And then I thought, you know, the Rolling Stones and the Beatles and all these guys, they're pretty old. They're even older, some of them, than me. Mick Jagger needs a prompter now because he can't remember the lines anymore of his songs, okay? And so if you do good stuff, age obviously doesn't play a role. I'm not so sure about Hasselhoff, though. But I said this all to you that you remember that equation, the Henderson-Hasselbalch equation, not Hasselhoff. Henderson-Hasselbalch equation is the equation for a buffer, okay? It's pKa, and I said this 10,000 times, logarithm of the conjugate base divided by the conjugate acid, okay? So, and here are the pKa's. You can select any of those, and you put here the conjugate acid in there, and here you put the conjugate base in there, and you get a nice buffer, and these buffers would be in these ranges. So you go in a book, you look up what are the pKa's, and you make your buffer, okay? All right. Now I'm going to... buffers, by the way, buffers. You ever seen that show, the Irish Travelers? No? There is some people who don't live in a solid place. They used to be called different. But if they come from Ireland, they call everybody who doesn't move around, they call us buffers, okay? We are the buffers. I don't know if you have seen that show on television, but you may remember that, all right? But this is not a buffer in this case, okay? In our common sense here. So now, fun aside, we have a solution of ammonia, NH3 solution, and I want to make a buffer out of this. And so if you look very carefully at the slide that I give you, the solution is already on there. Of course, the solution is right down here. Do I put in sodium hydroxide, sodium chloride, or hydrochloric acid in order to make a buffer pH larger than 7? What do you think? Okay, why don't you give me your answer? What would you put in there to make a buffer of pH 7? So obviously ammonia is a weak, what is it? A weak? Okay. So you mix a weak base and its conjugate. It's still fighting the buffer, you see that? Still not getting into the acidic region. All right, let's see. Okay, you're telling me that all this what I tried to tell you this lecture, many of you didn't get it, all right? It's very disappointing for me, all right, as well for you. So you take, this is the same thing that with the reverse meaning actually, that I have here, before I explained to you an acid and its conjugate base, okay? The acid was this here, acetic acid, and acetate was its conjugate base. Now I want a buffer that's in the basic region, and I want to make a buffer from ammonia. So I put NH3, and I put what in solution? So this is the weak base, and what is this conjugate acid? What is the conjugate acid of ammonia? NH3, what would be the acid? Ah, okay. Where do you get that H plus from? From here, or from here? Okay, why don't you discuss this with each other and give me a revised answer? It's just, now we're dealing with this with base, okay? I haven't explained it. Base would be this panel here, okay? I could go through this, and if I would be you, I would study base a little bit, okay? Not a little bit, very hard I would study it. Also the titration of a strong acid, of a weak base with a strong acid, okay? It's not? It's amazing, isn't it? It will, yeah. Okay, you can discuss it. You gotta get this stuff, please. I don't know what to do, what else to do. But you also will have to read the book, okay? Chapters, what is it? 8:4 to 8:7, isn't it? Or 8:5 to 8:8. Wow. You heeded my advice. That's good. So let's see how this all pans out here. So we have NH3 plus, that's our weak base. And the conjugate acid, so we put H3O plus here, that's H3O plus Cl minus, completely dissociated. So that makes, what does that make? Makes NH4 plus H2O. So that's the weak base, and that's its conjugate acid, all right? So that's your buffer, and with this you used HCl, okay? I think this should be it for today. Yeah, that's going to be the next time. All right, have a good Wednesday and Thursday. By the way, tomorrow at 5 o'clock here is review by yours truly, no, not yours truly, by Greg Dellinger. Yours truly is today at 4 o'clock at 446 Latimer, my office hour. Wednesdays at 4, Fridays at 3 at 446 Latimer. Also make use of the drop-in office hour here, down there. The drop-in office around the corner. In the final stretch, you need to get good now. Yes? Yeah,